Okay, so we are at lecture 21. Okay, can you see my pad?
Yes,
So,
sir.
so we need to do. I need to do one more lecture, maybe this current lecture on partitions. Uh, so, and then next time we'll start something else. So, what I plan to do, I wanted to do about 5 lectures of, uh, you know, symmetric functions. I mean, the main purpose of doing symmetric functions a little bit is that you will see it in some other courses, but I don't know how much we'll be able to cover to be able to do some, uh, of the important theorems. But in general, 1.5 hours is quite efficient and quite a lot. So I might be surprised. So I may not do many proofs and just do some results, just so that you become familiar, or at least I become familiar with these functions a little bit. So today the agenda is we want to cover this guy. And uh, uh, so this is Ramanujan's congruence, which most of you rediscovered. And in general, I would like almost all my courses to have at least one result of Ramanujan, but I don't know if it's possible in calculus. So I'm going to, so I prepared a certain approach, but I think I will change that approach and first prove this. So to prove this, we will show this proposition, and so we will show this shortly, but let me write it down. In minus. And then this is the theorem which we want to target. So what is this guy, first of all? Uh, if we just take n equal to npn, and then for m equal to 1, what am I getting? Okay, there's something missing here. It's times 2m plus 1. So for m equal to 1, I get a term. This is minus 1 raised to 0. M equal to 1, I'll get 3 times n minus 1 into 2 by 3, and p of n minus m equal to 1, n minus 1, minus the second term will be m equal to 2, so there is 5 here, n minus 2 into 3 divided by 3, p of n minus, now this is m equal to 2, so n minus 3 plus so on. So this is a recurrence relation. in terms of NPN. So what we will do is we will prove this theorem by using this proposition, and the proof is by induction. So when n is 0, so what I do is I replace this n by 5n plus 4 and put n equal to 0, then I will get p of 4 times p of 5. So for n equal to 0 here, I'll get 4 into p of 4. This will be 3 times n is equal to, this n will be equal to 4. So 4 minus 2 by 3, p of 3 minus 5 times n is 4 minus 2, p of 4 minus 3, that's 1. And then rest of the terms will be 0. So for m equal to 3, I'll get 3 into 2, that's 6, n minus 6. So it will be bigger than this. So in this term, the rest will be 0. So what is this? This is 12 minus 2, that's 10 over 3, p3 minus 5 times 2 times p1. So by this recurrence relation, you can see this 3 cancels. Each of these terms are congruent to 0 mod 5. Right? So for n equal to 0, it works because of this. I mean, we know that p4 is equal to 5. So we know it works in any case, but I'm just trying to say that even from this recurrence relation, it just shows. So now suppose it's true for some n. So now we want to prove it for, let's say, n equal to 5n plus 4. And it's true for smaller n. So then what do we have? We have this term minus 1 raised per m minus 1, 5n plus 4 minus m plus 1 over 3 times 2m plus 1. This is m bigger than equal to 1, and p of n minus n plus 1 over 2. So what I want to do is, all these terms are smaller than 5n plus 4. So if I can prove that this general term is 0 mod 5, I'm done. So consider the general term. For m minus 1 raised per n minus 1, 2m plus 1, 5m plus 4 minus m plus 1 over 3, and p n minus m plus 1 over 2. So now,
Professor,
yeah,
shouldn't you replace the n in the last term as well inside p?
yeah, exactly. 5n plus 4 minus this. Yeah, so now consider the following cases. So suppose m is equal to 4 or 5 mod 5. Okay, I'm going to show for all m, basically this term is going to be 0 mod 5. So for m equal to 4 or 5 mod 5, then this term p of 5n plus 4 minus, it's either 4 here times 5 here or whatever it is, uh, um, it's divisible by 5. So it's 5 times k for some k. And this is going to be 0 mod 5 by induction. So if I put 4 or 5 over here, then I'll get 4n plus 4 minus 5 times something. If I put 4 here, then this is divisible by 5, so it's 2 times 5. If I put 5 here, then this is divisible, this 6 is divisible by 2, and we get some 5 times k, right? So by induction, we are done over here. If m is congruent to 2 mod 5, then this term 2m plus 1 is congruent to 0 mod 5. So again, we are done. This whole term becomes 0. And if m is equal to 3 or 1 or 3, well, m is equal to 1, let's first take mod 5. Then what does this become? Uh, this is uh, this term 5n plus 4 minus uh, 3 into 4 over 3. So this becomes, so this 4 cancels, so this becomes congruent to 0 mod 5. And if m is equal to 1, this was 1, is it? No, this was 3. So if m is equal to 1 mod 5, then yeah, so 1, 2, 3, 4, 5. This is the only one left. So this is 5n plus 4 minus, now 1 is same as minus 4 mod 5. So I'll put, again, I'm looking at this term. So this is minus 4 times minus 3 over 3, which is again, uh, minus minus 4 will become, yeah, so this will be 5n plus 4, uh, 3 minuses, minus 4.
Professor, for m equals 3, how do we get the 0 mod 5?
Well, I replace m equal to 3 here, and then 3 times 4 divided by 3.
But it would
So,
be 3 mod 5, right? So,
well, I mean, this whole term over here is 5n plus 4 minus 4, which is congruent to 0 mod 5. So 4 cancels.
no, I mean, m wouldn't be necessarily divisible by 3, right?
No, m is, yeah, m is not divisible by 3, but yeah. So so okay, I get it. So anyway, suppose we have 5n plus 4 minus, uh, let's say 5k plus 3, 5k plus 4 over 3. Then you can bring the 3 over here. I mean, these are the rules of arithmetic that you can sort of just look at the numerator. Yeah, assuming the denominator is uh, whatever. Anyway, let's just try it. So for some k, it is this, right? And then we get 5k plus 3, 5k plus 4, and the whole thing divided by 3. And then uh, one gets what? 15n plus 12 minus 25k square, these two, minus 20k minus 15k minus 12 over 3. So this guy cancels. And then this is congruent to 0 mod 5. Because 3 and 5 are GCD is 1. So you can ignore this 3. That's the idea. So, I mean, how do I say it? The as long as the whole thing is divisible by the whole thing is divisible by 3 actually, if you look at it. But you can prove that if you wish. But these are also the rules of.
So, Professor,
Yeah.
for m is equal to 13, m is 3 mod 5, but a fraction is not divisible by 3.
Um, what are you saying? Say that again.
For m is equal to 13,
Uh,
m is 3 mod 5, but a fraction is not divisible by 3. Like it does not become an integer.
yeah, but still, I mean, if you do something like this, then it will. So these are. It will still be come out to 0 mod 5. So it should actually, but we can try it. So m is what are you saying? M is
13.
okay. So it's 13 into 14 over 3.
Yes, Professor.
And suppose you have some number here. Let's say which number? M is yeah. So I mean, how do I explain it? I mean, this is. Um, um, well, let's just first try it with something over here. Uh, so there's some chat happening. I think yeah, it is modulo division. So the thing is, in the end, the answer comes out to be an integer, then it's the same. That's how one argues. So let's try. Oh, what should we try? So let's take 5n plus 4. So let's take 9 minus this. So this is 27 minus 13 into 14 mod 3. And when you do mod 5, what does that become?
0.
How much is 13 into 14?
Professor, but
Yeah.
Professor, what I am thinking is like, how are we defining like the modulo of a rational number with respect to like an integer? Because I don't think we have the concept of finding like 5 by 3 mod 6 or something. Like I think we have only defined it for integers.
Yeah, but I mean, there is this arithmetic is there. I mean, p by q congruent to p prime by q mod something r if q and r are relatively prime, and you can do the same thing. So this is, I mean, I've forgotten exactly what the justification of all this is, but it works out. And that's how we do modular arithmetic. I mean, one way to look at it is that Q is invertible. It's an invertible element in this group, ZR. So suppose we are doing mod P. So in ZP, 3 is an invertible element. It's a unit in here. So you have some kind of a number which when you can multiply it, you get 1. So in this case, 3 into 2 is 6. So
Right.
if you multiply the top and bottom by this, then then you get this is 1 and whatever. So that's how it works. So uh, But I mean, this is a legal thing. So anyway, what I'll do is I'll find some kind of reference for this, maybe cover it later. I've forgotten exactly what you do in that, but I know it's done. So we can come back to it at some point. Right now, just accept the fact that it will become this way.
Okay.
Okay, so in any case, if you do allow me this one, then it does become, so for m congruent to 1, 2, 3, 4, 5, this general term becomes 0 mod 5, and therefore this entire sum becomes 0, and therefore by induction, because we use the induction hypothesis, and therefore this is true. So the proof,
Professor, can you repeat the argument for 1 mod 5, please?
for 1 mod 5, it's 1 is minus 4 mod 5.
Oh,
So I
right.
can replace m by minus 4 and minus 3, and then similarly get whatever I want to get. So I mean, basically I'm cancelling the 3. What I mean is I multiply by 2 on top and bottom mod 5, and then I get whatever I want. Okay, so is that okay now? Shall we go ahead? I mean, I'll get back to you a little bit on more details of this
Yes.
arithmetic. So essentially we have proved it. We need to prove this proposition. So we need to prove this kind of recurrence relation. It seems to be new. We haven't found it in the literature. So this proof is new also. Um, so now to prove this, I need to show you another trick using those matrices, and I need to do one more matrix. So this I wanted to avoid actually, but it is required for this proof. So you recall what we were doing. We took matrices like this, uh, and there was a sequence. I mean, we did 1 minus z q raised per k, we did 1 plus q raised per k, then we did a whole bunch of them. And what we did was we found a matrix A based on, which was very simple. So now what we want to do is, so we had a sequence of generating functions, and now what we want to do is consider this guy, which is kind of a very general uh, kind of matrix. So this is q infinity raised to the power bk. No, this is not q infinity raised to bk. Each term is raised to the power some sequence. And what I will need is basically when I need bk to be equal to some kind of a equal to k. This is what I will need. But this is called prefab. So this is a generating function of what Wilf calls prefabs. And the partitions, so I'll explain what this terminology is. So the partitions are called hands. I mean, there are two competing views on this guy. Uh, if you're reading Wilf, then this is what he calls them. And uh, uh, hands are made up of cards, and cards have a weight and a picture associated with it. And there is a deck of BK cards called primes for each K. So for each K, there is a deck of cards. Okay, so now let's connect it with the previous guy. So let xj, this be represent a set of all the primes of j. So let j1, j2, so on up till jbk be all the primes. Okay, and what we do is we think of, say, whatever for some b, we think of them as colors of j. So the weight stays same, and this picture is basically associated with colors. This picture is essentially a color. Okay, and these colors are allowed from this bk. So there are bk kind of colors. So I've written b, but what I mean is bk. Okay, and when I write xj plus xk as I was writing earlier, then I think of them as let's say ja plus kb. So sets like this, where ja belongs to xj and kb belongs to xk. Okay, and we had 2xj, that has to be looked at as xj plus xj. So this is like a multi-set. I have xj has many colors, and I pick one item from one here and one item from here, and I call that a sum. So now you can sort of imagine that I have a bunch of these numbers, and they all form a hand, and the weight is really the partition of that hand. Okay. So extend this by induction to this set which we were looking at, I going from 1 to n. Okay, so by a hand of size n, we mean some element pi belonging to this, such that uh, so ai elements are of weight I, so summation I ai is equal to n. Okay, and the number of elements in each xj is this bj, as we see. So this is the number of primes. So let me do an example. So this is a very generic thing. It actually includes lots of things like graphs and trees and graphs and all kinds of materials, which you can see in Wilf's book. But let me do an example from partitions. So these are colored partitions with k copies of k, which means k colors of k. And these are actually in one-to-one correspondence with what are called plane partition, which I will uh, just after a bit, maybe. I will define these separately. But first, let's just figure this out. So for n equal to 0, again, there's an empty partition. N equal to 1, we have x1. So there's one color of 1. So k copies of k. So only one color. So I'm just writing it as 1, 1. So 2 will have 2x1 and x2. So 2x1, there's only one possibility, but x2 has two possibilities. So there are two copies of 2. So one copy of 2, and so let me just count h of n here. This is 1, this is a blank 1, and now we have 3. Okay, for n equal to 3, so 3x1, x1 plus x2. So our counting approach goes is the same, except that they are sets. Now the numbers are increasing. Okay, and x1 plus x2 and x3. So 3x1 will just be this. x1 plus x2 is 1 1 plus 2 1 and 1 1 plus 2 2, right? And x3 has 3 items, 3 1 3 2 and 3 3. So 1 2 3 4 5 6 of them. So you get the idea? Is that okay?
Yes,
So
Professor.
so for some hand pi, so these are the hands. This is a hand, and in one hand you can, they're all adding. All these hands add up to 3. So they're like partitions of 3, and all these hands have got are made up of these whatever cards, and cards have a color and a weight. So weight is 2 and color is 1 here. Weight is 2 and color. So now you understand all this terminology in whatever Wilf is talking about. Colors, weight, picture, and all that. So his colors and is a picture. And this can be handled as easily as we were doing earlier uh, in terms of um, you listing them. So for a hand pi, let's define f k for some color of pi will be the number of uh, parts equal to kc with a particular in pi, and the frequency of k in pi, this is fk of pi, will be the sum of all the kc, where kc belongs to x k. So take all the k's if they repeat. For example, you may have 2 1 plus 2 2 2 plus 1 1. That's possible in 5. So you take the frequency of k, you include all of them, and fk n is the sum of all the frequencies. All frequencies of k in hands of weight n. So same as what we did earlier, we just add all of them. So for example, in here fk3 will be 9. Sorry, 3. So they're coming 3 times over here, and 2 is coming 2 times. So it's a little different from what we did earlier. Okay, but the same principle holds. So the proposition is HN and everything is as above. represent all the hands of size n, where k comes in bk colors. So xk is equal to bk. Okay, and then we have the recurrence relation fkn is equal to fkn minus k plus bk hn minus k. Okay, and the matrix equation is an, same matrix equation, h0 is equal to f1n, f2n, and so on, fnn, where the entries of A are given by AI of J is Bj, is Bi. If I, if I divides J and 0 otherwise. So earlier it was 1 when Bi was 1 for partitions, and this was P, and now we just replace it by P. So this follows straight from here, the matrix. Further, as usual, NHN is equal to summation K Fk. So these two guys determine everything. Okay, so basically we are generalizing this guy. So there was 1 here, and now I have put a bk here. That's all. And it's kind of surprising that the same matrix works essentially. It's not so obvious. I mean, this is the key idea that we have in this whole game, that this same thing works. I mean, we have a similar theorem for z over here. So you can also put a z, and then you have a z raised per r or something, whatever we had. And then this bk could be negative, remember? So we had a -1 here and a +1 here, and then it went up there. So that was allowed. So bk was allowed to be negative. So it works for any complex number, in fact. So the proof is not as it's more intricate than the previous one, but not particularly difficult. So let's just go through it. So for x equal to summation cj xj, j going from 1 to n, k with k, it should be n. Okay. So let x denote the number of hands in this kind of in this thing. So this is the formal symbol where we are taking these sets, right? Cj, xj, and let x denote the number of hands in x, and let fkx denote the number of k's in X. In hands in X. So consider the set of hands of weight n represented by, so I'm just taking out one of the k's here and then keeping the rest in y. J is not equal to k. Okay, so what I do is from this set I just take out the guy which contains xk in it and separate it out. Okay, so here we assume that ck is bigger than 0. So it has an xk in it, it has a k in it in some color. So we just look at those guys. Okay, so how many, what is the number of hands in X? How many are there? So we count it. So this is the number of hands in Y, and here I'm basically, let me write down the formula and then I'll explain. So here in this one, I'm just choosing CK items with replacement from XK. Right, so xk is the set of primes, is the set of all the numbers with various colors, and I have to pick out ck of them. Right, so for all these choices and every choice of y, I'll get a number of hands. So all the number of hands in X are going to be this much. Is that clear? Is that fine? So this, I mean, if you remember the formula, it was in your homework, it was ck plus xk minus 1 and then ck. And that's the same as this guy. Right, and this is essentially this, so I'm going to replace it by bk now. Bk minus 1, bk minus 1. Okay, now we want to relate x with the hands obtained by deleting. So earlier, by deleting 1k, 1xk. So so remember we went back. We want to prove something like this. So we deleted 1k, and then we came back to n minus k. And so I want to delete it, delete 1xk to relate it with fk of n minus k. So so the contribution of x to fk is, so for each of these hands I will contribute ck. I'll be contributing k, right? Yeah. So for each of these guys, I'll be contributing uh, uh, one ck k's. So that's the contribution, ck plus bk minus 1 over bk minus 1. right? And now we use the elementary identity. This is n plus k, choose k minus 1 equal to k, n plus k minus 1, k minus 1 plus n, n plus k minus 1, k minus 1. So we use this elementary identity to get fk of x is equal to ck minus 1, ck minus 1 plus bk minus 1 or bk minus 1 y plus bk, oops, so okay, so far I'm done nothing. I'm just counting what is the contribution of x to fk, and it's this, and then this is just splitting the two things. I write it as k plus n minus k, and then I get, I cancel a few things. So this is no, this is easy to calculate. This is easy to prove, and I get this. Now I look at both of these guys. What are these steps? Okay, so this guy, this chap right here, is this whole thing is essentially fk of x minus xk, because the contribution of x to fk is this. So just compare with this formula. If I have one less, xk, then I will get this exactly this. So ck minus 1. Replace ck by ck minus 1 in this formula, right? And this guy is number of k's. This chap, not the bk, but this guy is the number of k's in x minus xk. Okay. So this formula has to be compared with this guy. The number of hands in x with one less. So if I sum over all, if I now sum over everything, okay, if I sum over all the hands in, you know, so what do we do? Next we sum over all x that contain a small xk. If we sum this whole thing over all the hands, all the x that contain xk, we will get fkn on the left hand side, and this we will get fkn minus k, and here I will get all the hands of n minus k, right? Because I've deleted one xk from all of them. Is that clear? This is true for all partitions which are. So it's the same thing which we did, but little bit, you know, more complicated because we have to keep track of how many are there in each set. Does this make sense? Is okay?
Professor, I think we'll have to revisit it later to properly grasp it.
Okay. If you find a mistake, let me know.
Yes, Professor.
Yeah. So essentially, the confusing aspect is that each of these is a set of things. So if we are looking at all the number over here, then which the guys who contain CK, this is the total number. And now this number shows up over here, this one with CK minus 1. So once we have deleted one of the XKs, we get this relation for the remaining. So we delete. So if we have something which has an xk, earlier we were deleting one xk, and now we are relating it to the previous guys. So this chap is the same thing with that xk deleted, and this chap is the number of hands with one xk less. And then if we sum over all the hands that contain xk, we will get this business. So this proves it, and then the matrix is immediate. So matrix follows from, you know, if you do fk minus n minus k equal to bk h n minus k, and then you sum, you know, telescope it, and then you will get uh, the kf. So this is fine, and of course this is also okay. This is also the same. K h k. This follows from the definition. So again, each of these over each of these, this is as before also. So each of these guys for a particular partition will be equal to Hn, will be equal to n. So when you sum it, then it will be summing over all the hands or partitions. Okay, so uh, let me also, so I wanted to define what are plane partitions, because this particular you know, bk equal to k case is equivalent, but it's not so trivial to show that they are equivalent. So this is due to plane partitions were also due to McMahon, and he's the one who showed that they have this generating function. So what are plane partitions? Let me just define them, and then you can look through on Wikipedia. So you have something like this. So you have an array. Um, I guess K, whatever. So lambda is a partition. First of all, lambda, uh, which is lambda 1, lambda 2, lambda k is a partition. So a young tableau, it's a shape of a partition. And these numbers are placed, pi ij are placed in this tableau. and they are what should I say, non increasing in columns and rows. In columns and rows, and it's a part if summation pi, uh, so all these numbers ij is equal to n, it's a plane partition of n. So this is known as pi. So you have a partition, something like this, and then you have numbers placed over here which are um, non-increasing. That means, something like that. So everywhere you can't something like this. So decrease here, decrease here, decrease here, decrease here, decrease here. That's a plane partition. And it's not obvious. And the correspondence is not obvious. I mean, one has to work hard on it. So I'm not going to do
So,
that.
Professor,
Yeah,
so essentially what we are doing is we are just filling the Young's diagram with numbers, right? Says that the numbers
yeah.
would
In fact,
like
you can,
come up.
think of it as boxes. So I'm not very good at making the pictures, but you can think of boxes. These could be three in number, and so they're solid partition. I mean, they're, imagine three cubes on top here, two here, one here, one here, three here, two here, one here, and so on.
And Professor, these need to be integers.
Yes, yes.
Okay.
So yeah, I don't know how to make it in the. I don't know how to draw a picture, but you can imagine that these are uh, basically they are. Oh, I'm not going to try. So there are three boxes here, then three. So three stacked here, uh, two stacked here, one stacked here, one and one. So you can, all of these are partitions. So three, then three, whatever. I want to go to Wikipedia and see the what nice pictures. I know how to get them in LaTeX. So actually, it's quite useful now to have LaTeX for somebody like me because I can draw pictures without bothering to be a good in drawing. Anyway, the other case which we want to do is when BK is fixed, R colors. Okay, so then we have this kind of equation, which is q infinity raised to the power r. So, for example, r is equal to minus 24. Um, and if I multiply by q, then this is known as tau function. Have you heard of that? Tau function.
Not really.
Huh?
No,
So,
Professor.
sorry.
No, Professor, we haven't heard of it.
Okay, so this function tau of n, Ramanujan worked on it and he made several conjectures. So tau n is a multiplicative. So Ramanujan made these conjectures that it's a multiplicative function, so it's a number theoretic function. And one of the things he said was that this is true. for a prime number, something like this. And this was proved by Deline, and he got a Fields for it. And if you prove this, then you will get a Fields medal. Provided you do it fast enough. So this is Deline's conjecture on tau of n. Now, so this is the reason why this approach is quite interesting. Whatever we are doing, that it has a very systematic and same approach works for partitions as for things like the tau function. Okay. So anyway, if we do for fixed r, what are we saying? So for fixed r, so when I say that try this, you should seriously try it. At least you should program it, convince yourself what it's looking like. You never know, you'll get some idea at some point in your life. So I mentioned this to my calculus class that when um, Wiles got his, you know, started work on his problem when he was a schoolboy. And then he kept learning math, kept learning, but he was always guided by the fact, the hope that he would be able to solve Fermat's last theorem. And he did it. I mean, eventually he did it. So you keep, all great mathematicians try a bunch of problems for a while, and they have some idea of when what is required to prove them. Okay, this is very tough problem, but some intuition they have. And this is this. If you're a math student, then this is what you do. I mean, you go to Wikipedia, found out about problems, you try a little bit here and there, get some intuition. Then you understand a lot of other maths, because everything in math is basically related to trying and finding some solution for somewhere coming close to these kind of problems. There are a handful of problems actually which people are chasing. So yeah, I mean, it's much easier to do now than it used to be in my time. And in fact, so I see bright young mathematicians, and when you talk to them, you realize that okay, they're in the game. They know all these problems. They are figuring out how to come close or whatever. Anyway, fixed k. What are we saying? Let's call this PR. Hn as PR. So let's say this 1/1 minus q raised per k raised per r is Prn q raised per n. Okay, and we know that, or we can just call it P. Well, let's keep it PR. So we know that this is a matrix, right? And here it's PR n minus 1 and so on up till PR 0, and whatever this function is, F1R n Fnr n. So this standard equation, and so I'm going to play with this guy, and the goal is to find in less than 20 minutes this recurrence relation. Okay. So I hope by doing the homeworks and all that, you have become somewhat familiar with this type of equation. And what I'm doing right now is I'm going to multiply both sides by by 1, 2, 3 up till n, this vector, and then I'm going to sum over all the columns. So I multiply by this guy, I'll get ones here, you know, I'll get ones here in the first row, then 2 in the second row, 3 in the third row, and so on. So when I multiply by both of these and then I sum the columns, I get, what do I get? I get R sigma 1, 2, and so on, R sigma n, sigma 1 n, sorry. Then I get PR n minus 1, PR 0, and here I get basically summation k f k r n. So, and what is sigma 1 of k? It's the sum of divisors of k, right? Because the numbers are non-zero only when they are divisors. So the second one will be non-zero, 1 and 2 are non-zero, 1 and 3 are non-zero, and here it will be 1 and 2 and 4 will be non-zero, right, in the fourth row. So only the sum of divisors basically of n. So the nth column, the kth column will be the sum of divisors of k, and I get this. And then this is your usual uh, uh, you multiply this over here. So r times sigma 1 of k and PR of n minus k, this k bigger than equal to 1, and this guy is your n PR of n. This is working, right? Is this okay?
Yes, Professor.
So in this one, if k is 0, we can take sigma 1 of k to be equal to sigma 1 of 0 to be 0. So I could go from k going from 0 to whatever. And in terms of generating functions, this is a convolution. So suppose we take generating functions. If we take generating functions, what do we get? We get r times summation sigma 1 k q raised per k, and now it's over k times summation p r n minus k uh, q raised per no q raised per k, right? And this is summation k p r k q raised per k. So both sides I'm just taking generating functions. On the left hand side, since it's a Cauchy product convolution, we just get this. Is that clear? Yeah?
Yes, Professor.
Is this okay?
Yes, Professor.
So this we've done a million times, right? Now what I do is I multiply both sides by so this is interesting that this r comes outside. I mean, that's the key idea. What I do is we multiply both sides by another such guy. So I multiply both sides by PSN q raised per n going from 0 to infinity. So I multiply both sides by this guy, I mean, I know what this is. This is just the product 1 minus q raised per k into s, right? I know what this is, but I multiply both sides, and then what I do is I use this guy itself, uh, you know, to eliminate this chap. So this same thing with s is also holds true. So let me just write it and then you'll see. Well, let me just do it. So this is r times summation sigma 1 k q raised per k times, I'm going to put this one in the middle, summation ps n q raised per n in the middle, then pr n q raised per n n. This is equal to, so I'm multiplying here, summation k pr k q raised per k. How many k's and n's are there? I mean, this isn't. You could just multiply by k here, I guess. This is a problem anyway. Just keep it k. Summation ps k q raised per k. I mean, it doesn't matter what we're doing, but okay. Now these two guys I combine using this chap. So except that I don't have an R and I have an S, so I have an extra. So these two chaps I had combined, and what I need to do is I need to multiply and divide by S, and then when I combine it, I will get uh, K P S K q raised per K times K P raised per R K q raised per K. Okay. So what's the deal? I mean, what have we done? So if you notice, we have K times PS here, and here we have K times PR, and we interchange the R and S in some sense. So some kind of a, you know, um, interchange has happened, and then we have R over S. Now again I do, uh, you know, um, what should I say, a convolution. Multiply these two series together. So let's do q raised per n together, and let's do j going from 0 to n. So let me be careful here. I want j times psj and pr n minus j. So this whole thing multiplied by q raised per n and then sum over n, and again n going from 0 to infinity, and again this time again I want the psj here. So psj, and now n minus j is inside here, pr n minus j. Okay, all right so far? Is that fine? So now,
Kind of.
huh?
Kind of, प्रोफेसर इज जस्ट रिविजिट लाइक बाद में वापस इसको एक बार देखना पड़ेगा पूरे प्रूफ को.
I mean, from this step to this step, it should be clear that you're taking one j, one n minus j, and then one j and one n minus j.
Yes, professor, this part is clear.
Right, and then I mean, you know, I have this. Uh, I keep one of my friends in Vienna. We go through various lectures. We used to go through together, and I couldn't get the whole thing. And then I used to say that I understand locally what happened. I don't understand globally. Globally might happen later, but at least locally should happen in the class. That in every neighborhood of a step, you should know what has happened.
Yes, Professor.
Okay, so follow that much at least. Okay, anyway, so we compare coefficients of uh, q raised per n, and then what do we get? We get bring everything to one side, and remember that n minus p of pr of negative is taken to be 0. So I just bring everything on one side, and I write sum on j going from 0 to infinity, and this term is common. Psj and Prn minus j is common, and I'm bringing n minus j minus this j times rs, and this is equal to 0. So this is my final result, n minus j. No, I should be 1 minus rs or 1 plus rs. So did I do something wrong? Am I getting? I should be getting. In my notes, I'm getting 1 minus rs over here. Well, maybe I'll make a mistake. We'll figure out if this is a mistake. But so far we are getting this. Okay, so this is the main result. This is one of the main results, and now we specialize. Ah, that's fine. That's fine. So what we do is we take s equal to minus 3 and r equal to 1. So r equal to 1 means PRN becomes P of n, and s equal to 3, s equal to minus 3 means that we are looking at this guy. And here I want you to recall one of your homework problems due to Jacobi, which you had to verify. And this is what the answer was. Yeah.
Yes, Professor.
So this was due to Jacobi. So what is PSJ? PSJ is minus 1 raised per m, 2m plus 1. If, I mean, PSJ was a coefficient, right? If j is equal to m into m plus 1 over 2 and 0 otherwise. So you notice n minus j I'm taking, and this j is mostly 0. This PSJ is mostly 0, and that's why I'm getting a nice quick recurrence, just like Euler. That was the goal, to get here, and R has become uh, partition. So what do we get? We get summation m going from m bigger than equal to 0. Now I'm going to go to this m 2m plus 1, n minus j, uh, well, j is this guy, m plus 1 over 2, times r by s plus 1. So r is 1 and s is minus 3. So minus 1 by 3 plus 1. So that's 2 by 3, right? And ps is, I've already included what ps is. And pr is pn minus n plus 1 over 2. So we get this guy, and let me just take out the m equal to 0 term. So when m is 0, um, I get 1, then I get n here, then I get pn here. All this goes away, and I bring all the other things to the other side. So I add a minus sign, and this 2 cancels, and you have m into m plus 1 over 3 p of n minus m plus 1 over 3. So I get this. This is equation 3. Is that fine? Is that okay? And this is the recurrence we began the lecture. So where are we? I said we will prove this guy, and from this proof we derived this theorem, and this is what we got after all this story.
Professor, I'm just thinking, like, how do people even come up with such proofs? Like, there's just so many steps happening here.
Well, um, so I mean uh, okay, I'll stop sharing to answer this question. Um, so I mean, we are basically I can describe to you how we started. I mean, we started by some other project. We started with some other project where we were doing this calculation with these xi's, and there were prime numbers actually we were working on. So that paper is already out, where we were calculating the numbers in these prime numbers, and then for some reason my collaborator and I, we kept going, and we realized that this is a easy thing way to do partitions. So I was not really in the game in partitions, you know. I mean, I'm very good at this Q series business, but I don't know enough about partition. I didn't know enough about partition, so I needed a way to handle this, to understand stuff. So every day we would keep doing, and then this A business started growing. So once we realized that okay, you can do odd partitions, you can do ordinary partition, odd partition, distinct partition. So we keep going on. Can we do this? Can we do that? So as it progressed, we realized one of the big things which was missing was that we didn't have a way to calculate the number of parts, and those also can we could do it. So all these things can be computed on the computer and check, is it working, is it not working. So we added a z, we added a -1. So after all this while, we got a calculus of how one could do it, and we did a million of these proofs like I did in front of you. So we did even more. And then the game became, okay, can we do something, can we allow it, I mean, can we do get something else out of it, I mean, why are we doing it, how do we get it published, I mean, to publish it we need to prove something which is nice. So if all the, so one of the things which came out was, what we realized was that this tau function business is there all the place, right? So tau function has got a lot of congruences. So we tried to prove congruences for anything, and one of this trick basically came out where we interchange the R and S, and one could get a congruence for partition. Then the question is, what good is that congruence? So one of the standard theorems is P5n plus 4. So in fact, my collaborator tried it. He figured out that it works. We're still working on it. We don't know whether more can come out of it or not. But now we've reached tau function, we've reached this, so we know that the theorem is important. So yeah, I mean, to answer your questions, this one just arrived. Many times you just discover a theorem and then you just try to prove it, and then as you get more and more into it, you say, if I know that, then I can do this, if I know this, I can do that, and we keep going backwards and forwards and making pictures, and then you get this huge. Most proofs you see in the papers these days are very highly technical. They're not so easy. But you are pretty much convinced it's correct, and then you just push it. I mean, you work on it. So my advisor used to say, once you know something is true, then you can, you know, then you'll figure out a way to nail the sucker. That's how he used to say. But first we have to know what is true, what we believe is true. So, for example, I still haven't got a proof of my own of Rogers Ramanujan identity. I worked on it on and off for the last, I don't know how many years. It, it has led to some papers. I've looked at all other proofs. Every time I get an opportunity, I look at some other proof. I want one of my own. I haven't got it. It's a tough problem. I know, Ramanujan's proof, Rogers proofs. I want something of my own. So there are all kinds of, you basically, you know you so many proofs are, you understand the fundamental nature of an object and you will get the proof. Okay, you play around on the computer, try to understand what it means, you will understand how to prove it. So most of the
Right.
proofs that you see in your uh, undergrad are of this nature, where you just understand what it means and you get it. But when you're doing research, then you don't know what is the fundamental nature. So you're just trying to somehow get a proof. And you look at, I mean, it's not so tough. Getting a proof is not tough. Getting a result is tough. Well, nowadays getting results is also easy because you have a computer. But so both sides are there. So I don't know if I've answered your question, but yeah, I mean, this is one of the pleasures and joys of being a mathematician. You work on problems and then there, it takes a long time to get something done. So even now, I mean, you saw how rough it was in my own head because I haven't really processed it completely myself. This is the first time I'm presenting this proof. So I've hardly typed it. I just typed it in a paper. So I don't even know it so well myself.
Right.